All right. So namaste everyone and welcome to lecture 8. So let us first do a quick recap of what we have seen so far. Okay, so in the previous class, if you remember, we defined this set of P boundaries, which we use the following relation to define. We said BP is the image of this boundary operator daba P plus 1. So for every P, which is an integer, BP is defined in this way. Similarly, we define the set of P cycles. So this is the set of P boundaries. This is the set of P cycles. Okay, so ZP is defined to be the kernel of daba P, right? And we also saw that BP ZP satisfy the relation that is stated over here. That is, BP is a subset of ZP and ZP itself is a subset of CP, right? So recall how we showed this relation. So we showed this relation by proving that daba2 is identically sorry, I shouldn't say daba2, the composition of daba with itself, okay, that is identically equal to 0. And I sort of spent some time explaining, okay, the way to interpret daba 2. Okay, so I said that this is to be interpreted as daba p of daba p plus 1 of c identically equal, I mean this equals 0 for all c in cp plus 1, and this is true for all p, right? So all p in the set of integers, right? So if you sort of apply this daba operator, okay, successively twice, then every chain in CP plus 1 would be taken to 0. So using this, we somehow said that this BP must be a subset of ZP, and ZP is the set of P chains which lie in the kernel of daba P. So this trivially must be the subset of CP, right? So while the subset relations are trivial, what is also important to note is that they are not just subsets, they are in fact subspaces, which means that BP is a subset of ZP, but BP is a vector space in itself. Similarly, ZP is a subset of CP and ZP is a vector space in itself. Okay, so this is a vector space, this is a vector space, this is a vector space, and this in fact is a subspace of ZP, and ZP is a subspace of CP. Right. So using this BP and ZP, we sort of proceeded ahead and defined this pth homology space. Right. So the way we defined it was HP is the quotient of ZP with respect to BP. Okay. So this is what was the relation that we used. So this was the relation that we used. Okay, and I also formally defined, okay, what this quotienting operation means. So it means that HP is the set of all equivalence classes. So this is the way we write it. So it's the equivalence class of every element C, okay, which is P chain, right, which lies in ZP, right? So you look at the equivalence class of every C in ZP, right? And the way we define equivalence classes is, so the equivalence class of a P cycle, right? So C is a P cycle. So the equivalence class of P cycle is the collection of all those P cycles in ZP which are equivalent to C, right? So it is the collection of all C prime in ZP such that C prime is equivalent to C, right? So C prime is equivalent to C, and C prime equivalent to C means that C prime minus C must belong to BP. Okay, so this is the algebraic relation that defines, when two elements are one and the same. Okay, so last time one of you asked me, right, why is this relation sort of used to define the equivalence relation? Well, the way to interpret this quotient operation is that we are trying to set every element in BP to be 0, right? So we want to in some sense ignore the elements of BP because if you remember, these are the uninteresting P cycles, right? So every element in BP, right? So BP is a subset of ZP. So every element in BP is also an element of ZP, which means that every element in BP is also a P cycle, right? However, those P cycles are uninteresting because they come from the boundary of this P plus 1 chains, right? Or they come because the daba P plus 1 operator is applied on the P plus 1 chains. They are interesting because in some sense they characterize the filled cycles, right? So this characterizes the filled cycles. So we want to somehow ignore this subset in ZP. And the way to ignore this is to somehow set every element in BP to 0. Right, so that's roughly what this quotienting operation is trying to do. That is, it is setting every element in BP to 0. Now, since we have defined this new 0 element, and if you sort of recall basic mathematics, right, we always require that 2 plus 0 be 2 for every element, and in general we require that r plus 0 be r for every element, r, right? So we require such a relation should be true, right? And now what we have done is that we have somehow set every element in BP to be 0, and so because of this reason, if you try to generalize this relation to this context, now you will see that every element C prime and C, okay, which are somehow different only by an element in BP, we want to think of them as being one and the same. Okay, so this is very similar to what I have written over here, and that's the reason this relation in some sense captures the fact that we are now trying to set this elements in BP to be 0, and we don't want to distinguish elements in ZP which only differ by an element in BP. Right, so this is loosely what we have done over here. Now the question comes, why do we want to set the elements of BP to be 0? Well, the set of elements in BP we want it to be set to 0 because these are the uninteresting p cycles, and in some sense we only want to look at the interesting p cycles in ZP, right? So the ones that are left, those are the ones that are interesting to us, and in some sense those capture the p plus one dimensional holes in the given abstract simplicial complex, right? So in that spirit we said the pth Betti number, which we denote by beta sub p, right? This we define it to be the dimension of HP. Now recall that since HP is obtained by taking a quotient of ZP with BP, and both ZP and BP are vector spaces, okay, the quotient operation will output a vector space. So HP itself is a vector space. In particular, it will be a Z2 vector space. Hence, we can talk about its dimension. And we said that the pth Betti number would be the dimension of this vector space, and this beta p, okay, which is the pth Betti number, will tell us the number of p plus one dimensional holes. Is this okay? So let me pause here for a couple of seconds. This was just a summary of what we did last time. Okay, nevertheless, if you have any questions on regarding this, please raise your hand, and this may be a good time to ask. So it's surprising that nobody has any questions. Okay, I mean, when I was a student, we used to ask several questions. I'm surprised that this is such an interesting topic, but very few of you seem very intrigued by it. Yes, Rankit, go ahead if you have a question.
Yes, so just for confirmation, the example you gave in the class of the two triangles, one was filled and one was hollow. So yes, by removing this BP, we are basically differentiating among these, right?
Precisely, that is what we are trying to do, and we will sort of later on in today's class itself try to compute the homology groups associated with these two simplicial complexes, and make sure that indeed what you have in mind, which is at present only an intuition, okay, we will make sure that these computations formalize our intuition. Okay, so we will look at such a calculation. Okay, so so today's class will focus on examples. Okay, so we will do a bunch of examples, please stop me wherever you think a step is not clear. Some of your exam questions, some of your assignment questions will be such examples. Okay, so if there is any step that is unclear to you, please stop me and ask me. Yes, Durjati, go ahead.
Sir, I want to say that I can't see the lecture note of this. Have you shared it?
You mean on the file section?
Yes, sir.
Okay, so unfortunately I got a bit late today, so I couldn't share the file section. So today's lecture notes are not available. Okay. All right. So let's advance. Okay, so if you remember last time we started off with this very basic example. So I agree that this is a very basic example, but nevertheless let's solve this basic example rigorously. Let's get our hands dirty, okay, and try to compute the homology groups associated with this very basic example. Okay, this itself has several interesting facets. Okay, once you get familiar with all of them, okay, computing the homology groups associated with a more complicated example is just a more careful analysis. That's all. Okay, but you will, in this example itself, you will see there are interesting facets that come out. Okay, so let's try to go over this example carefully. So let's try to understand what this example is. So this is a simplicial complex, right? So this simplicial complex just has two vertices. That's it. It has no edges, no triangles, and so on, but it just has two vertices. Okay, that's it. And we would like to compute the homology groups that are associated with this, right? And as we saw, okay, we can either compute in the usual homology sense or in the reduced homology sense, but we began with the usual homology computation last time. So recall, in this case, C minus 1 is 0, right? So C minus 1 is said to be the trivial vector space, and since there are no higher dimensional faces, right, here CP is 0 for all P bigger than equal to 1, right? And similarly CP is 0 for all P less than equal to minus 2, right? So this is the setup that we have, and under this setup we would like to compute the homology that is associated with this simplicial complex. Okay, so last time we sort of began this exercise and we looked at the case where P is less than equal to minus 2 and P is bigger than equal to 2, and we showed that this Pth homology group in each of these cases is actually a trivial vector space, right? So we saw that in all these cases HP turns out to be something like this, right? So so HP by itself is a set, right? And we sort of define this addition and scalar multiplication operation, and thereafter one can conclude that this actually is a trivial Z2 vector space. Okay, so I would like to emphasize something about the notation. See, when I want to talk about the field Z2, I will put this line there. However, when I want to talk about the set of kernels, okay, I will not put this this line over here. Okay, so based on that, it should be clear whether I'm talking about the field or whether I'm talking about the set of the kernel of a this boundary operator. Okay, so from that it should be clear. All right. So now in this example, it remains to determine the Pth homology group for P in this set, that is P either being -1, 0 or 1. Okay, so we will take these cases one by one, right, and see what happens. Okay, so first let's begin with the case that P is 1, right? So let's begin with the case where P is 1. So if P is 1, our goal is to compute H1, right? So H1 is Z1 quotient B1, right? So this implies we have to look at these three set of P chains, right? So first is C2, next is C1, and thereafter there is C0. So this should be C0, right? So you sort of go over here. This is DABA 2, this is DABA 1 over here, right? And Z1 is defined to be the kernel of DABA 1, and B1 is defined to be the image of DABA 2, right? So this is what we are going to do. So first let's try to write down what C2, C1 and C0 all are. So C2, C1, these are all trivial vector spaces. Okay, why are they trivial vector spaces? Because we set them to be trivial vector spaces. Why do we set them to be trivial vector spaces? Because in this example there are no higher dimensional faces. Okay, so that's the reason we set this to be the trivial vector spaces. Okay, so the next thing we observe is that C0 is the vector space made up of these four elements: 0, V0, V1, V0 plus V1, right? So these are the different zero chains that are present in the given simplicial complex. Okay, so these are the different vertices in this simplicial complex. So using this you can construct these different zero chains. All right, so now let's compute Z1 and B1. Sorry. So let's compute the Z1 and B1. So the first thing we do is we compute B1. So what is B1? It's the image of DABA 2. Now let's see what is DABA 2. DABA 2 is the boundary operator that goes from C2 to C1. right? And in this case, both of them only contain the element 0, right? And DABA2 maps 0 to 0. So the image of DABA2, okay, will just be the set containing the element 0. Is this okay? So I would like to emphasize that this is the element in C1. All right, so this is B1, right? So please stop me if there is any step that is unclear. In my opinion, these steps are quite trivial. However, if one of you finds it, something missing, or if you think I have made a mistake, please feel free to stop me, and I'll be happy to hear you out and make sure my arguments are correct, right? So this is how I computed B1. The next thing I need to do is I need to compute Z1, right? So what is Z1? It's the kernel of DABA1. Right, so DABA1, recall, is the map between C1 to C0, right? So C1 only contains the element 0, whereas C0 contains 0, V0, V1, V0 plus V1, right? However, this 0 is only mapped to 0. Right, so because we require that this be a vector space homomorphism, so it is important that 0 gets mapped to 0. Hence, the kernel of DABA1 only includes the element 0. Right, so we have finished computing B1, we have finished computing Z1. So now we should be in a position to compute H1. So H1 is the equivalence classes of all elements that are there in Z1, and Z1 only has one element, so we only have to look at the equivalence class associated with that element. The equivalence class of 0 is all those elements in Z1 which are equivalent to 0, right? So Z1 only contains this, and one can see that this element is indeed equivalent to 0, and the reason is that 0 minus 0, okay, this is 0, and this indeed lies in V1. Okay, so this is the way I have computed, and one can see that H1 as a set only includes one element, and that element is the equivalence class of the 0 1 chain, right? So this is the 0 1 chain, and this is the equivalence class, right? So it only contains one element, and one can ask, what is the addition operation and the scalar multiplication operation. So I have defined this repeatedly, that the addition operation is 0 plus 0. This is the equivalence class of 0 plus 0, and this is 0 itself, right? And in the same way, you can define the scalar multiplication operations, and based on this, one can see that this is a vector space. In particular, it is a Z2 vector space, and since it only includes the 0 element, or this element which acts like the additive identity, one can think of this as the trivial vector space, right? So so I can ask you whether H1 is equal to C1. Right, so can one of you volunteer and tell me, is H1 equal to C1? So recall, C1 is made up of so C1 we defined in this sense. So can one of you volunteer and tell me whether C1 and H1 are one and the same? What would your answer be? Yes, Durjati, go ahead.
Sir, they are not, sir, because H1 represent equivalent classes, and the C1 represent a singleton element.
Okay, so so you are right, Durjati, but let's be a bit more specific, right? So in C1, it's a set made up of the element 0. H1, on the other hand, okay, is made up of, so H1 also is a set, and the elements of H1 is another set. Okay, so the element of H1 is another set which includes this 0 over here, right? So the difference between C1 and H1 is that C1 has an element 0, whereas H1 has a set which includes the element 0. Okay, so that is very, very important to be able to distinguish, right? And the second thing we have to note is that while these two sets are not one and the same, they are isomorphic. Okay, so they are isomorphic because if I sort of map this 0 element, right, to this set over here, okay, the behavior can be viewed in the one and the same fashion. Okay, so that's the reason while H1 and C1 are not the same, H1 is isomorphic to C1. All right. Okay, so I hope you are able to now also appreciate this notion of isomorphism. While I would like to think of H1 and C1 as one and the same, but as sets they are not one and the same. However, this notion of isomorphism allows me to think of them as one and the same. Okay, so I hope that is clear. So the fact that this H1 is the trivial vector space, which means that it only includes the additive identity. From that one can conclude that the basis is actually the empty set, and that's why beta 1 is 0. That is, the dimension of a trivial vector space is 0. That's why beta 1 is 0. So now recall what our goal was. Our goal was to compute HP for P in 1, 0, -1. So we have finished 1. Now we will focus on the -1 case. Okay, so let's look at this -1 case. So again, here C -1 is so I mean in the P equals -1 case, we have to look at what is C 0. We have to look at C0, C -1 and C -2. Okay, so this is how the boundary operators, sorry, I have to be careful. So this is DABA 0 and this is DABA -1, right? So this is how the boundary operators are defined, right? So in order to compute H -1, I need to understand the story that is happening between these three vector spaces. All right. Okay, so C -1 is the trivial vector space. C0 is made up of these four elements, and C -2 again is the trivial vector space, right? So first let's compute Z -1. Right, so Z -1 is the kernel of DABA of -1. So since this is made up of only 0, this is also made up of only 0, and 0 gets mapped to 0, the kernel of DABA -1 will only include the trivial element, which is 0, right? And on the other hand, so let's look at this DABA 0 operator. Okay, so C0 is made up of 0, V0, V1, V1 plus V2. This is what C0 is made up of. And C1, C -1 is made up of only 0. And the DABA 0 maps everything, every element in C0 to 0. Right, so that is the how DABA 0 operator is defined, that it maps every 0 chain to 0. Okay, so that's how it maps. So since every element is mapped to 0 and C -1 only has 0, the image of DABA 0 will also only include 0. Okay, so notice that image of DABA 0 is every element in C -1 that is mapped from C0. Right, so one can see that from this relation over here, the image of DABA 0 must be 0 only. Right, so from this we have managed to compute what Z -1 is and what B -1 is, right? And from this it should be easy to see that H -1 must be made up of only the equivalence class of 0, where the equivalence class of 0 is the set that only includes the element 0. All right. Okay, so from this again one can conclude that beta -1 beta -1 is 0. Right, so what is the story so far? So in this simple simplicial complex which has only two vertices, beta p is 0 for all p not equal 0. Okay, so that is what we have managed to show so far. Right, so on one hand, this is an algebraic exercise, but at the same time notice that beta p turns out to be 0 for all p not equal to 0. So which is good for us. It is good because it is saying that this simple simplicial complex doesn't have anything or any interesting patterns from the perspective of homology for all p not equal to 0, right? Which is indeed what we would expect, right? So doing the computations algebraically is one thing. On the other hand, making sure that what the results that we are obtaining match our intuition is also very, very important. So I hope you are able to appreciate that beta p turning out to be 0 is a good thing, right? It's good because this shows that this simplicial complex doesn't have anything interesting in for p not equal to 0. Okay, so all that now remains is to discuss the p equals 0 case. So one hopes that at least in the p equals 0 case, beta p turns out to be some non-trivial number, right? Because for every other p, okay, beta p turned out to be 0, right? So we hope that at least in the p equals 0 case, the beta 0 turns out to be something interesting. Okay, so let's try and see what it will turn out to be. Right, so we look at the p equals 0 case. So for p equals 0 case, we have to look at C1, C0, C -1. So here is the DABA 1 operator, here is the DABA 0 operator, and we have to sort of look at what happens over here, right? So the first thing we will do is we will compute V0, right? Okay, so we will compute B0. So what is B0? It's the image of this DABA1 operator, right? So this is made up of the C1 is only made up of the trivial element 0, right? And C0 is made up of 0, V0, V1, V0 plus V1, right? However, 0 only gets mapped to 0. Hence, the image of DABA1, right? The image of DABA1, which is what B0 is, right? It will only include the element 0. Is this okay? So this is the set of elements in C0 which get mapped under DABA1, right? However, one can see that only the 0 element gets mapped under DABA1. So B0 only includes 0. Okay. So now let's look at what Z0 is, right? So as we saw before, right, this DABA0 operator maps everything to 0, right? So C minus 1 only includes 0. And DABA0 maps everything that is there in C0 to 0, right? So because of this reason, I hope you agree that Z0 must be C0 itself. C0 contains all 0 chains and Z0 is basically all those elements that get mapped to 0. And since this DABA0 maps everything to 0, it follows that Z0 must equal C0. Okay, so let me pause here for a second or two. If there are any questions with regards to how B0 turned out to be this and C0 turned out to be this may be a good point. Yes, Jacob, go ahead.
A one hole represents a two-dimensional hole, right? Like
Sorry, I
a
didn't
closed
hear.
figure. Yeah, a one hole means a closed figure without interior field, right?
So you are asking what is a one-dimensional hole? Is that your question?
Yeah.
So that is something we haven't defined, right? Because intuitively it's not clear to us what it sort of captures. So what we will do is we will first do this recipe, try to figure out what it gives us, and from that try to imagine what a one-dimensional hole means. Is that okay?
Okay, and okay.
So we haven't done it because we don't know how to do it. Okay, at least when I started reading, this topic, I couldn't really imagine on my own, okay, what this one-dimensional hole means, right? A two-dimensional hole means something like this. So you somehow construct this figure, okay, and somehow imagine something that is hollow like this. Okay, so I'm being a bit vague here. Okay, but when you sort of study any subject, you don't really have nice understanding of things. So you start off with a vague understanding. Okay, then you do some calculations, then you sort of sharpen your understanding about different things. So at this point, at least when I began this study of this topic, I also wasn't clear what a one-dimensional hole means. But nevertheless, I encourage you to think what it could mean, right? So I want you to somehow generalize this idea of a two-dimensional hole to a one-dimensional hole, right? So if you can generalize that, and then if you see if whatever answer we get, if it matches the answer, then in some sense you can corroborate that your guess and what exactly is happening, they have some relationship. All right. Okay, but at this point, what I want you to appreciate is that this B0 is is the set which only has 0, whereas this Z0 has every element in C0, right? So this Z0 is made up of 0, V0, V1, V0 plus V1. All right. So now we need to compute the quotient of Z0 with respect to B0. Now Z0 has 4 elements, so I have written down the equivalence classes of all these 4 elements. So this is the equivalence class of 0, this is the equivalence class of V0, V1, and so on and so forth. Okay, and now we have to make sure that all these equivalence classes, what they are and if they are different or not, right? So these are sets, right? So if some of these sets turn out to be one and the same, then I don't have to repeat it, right? So I hope you agree that the set 0, 2, 2 is the same as set 0, 2, right? So this is, I mean, the basic of set theory, that if a set gets repeated, I don't count it more than once, right? So I have to ensure that these 4 elements that I have listed over here, they are indeed different, right? So so let's try to first understand what these 4 equivalence classes are. So the first equivalence class is that of 0. Well, so recall the way we do it. So the equivalence class of 0 is all elements in Z0 such that C is equivalent to 0, right? This is the equivalence class of 0, and more formally this is all elements in Z0 such that C minus 0 belongs to B0, right? And this is equivalent to C in Z0 such that C belongs to B0, right? So from this one can conclude that we require, so this is, I mean, notice why am I writing it in this way? So this is the reason I am writing it in this way is that B0 is what we are using to take this quotient operation, right? So that is what I am doing over here, and we are trying to compute the equivalence class of 0. That's why the equivalence class of 0 will basically include every element that is there in B0, right? So again, you can see from this relation that we are trying to set every element in B0 as the new 0 set, right? Or the new element that we will think of as 0, right? So this relation again tells the point that I raised previously, right? So let's look at the equivalence class of 0. So since B0 only contains one element, which is the 0 element, right? So B0 only contains one element, which is the 0 element. From there it follows that the equivalence class of 0 is the set which only has the 0 element, right? So now let's move on and let's try to compute the equivalence class of V0. So the equivalence class of V0 is every C in Z0 such that C minus V0 is belonging to B0, right? So this is what we require. Right now, you give me an element in Z0 such that C minus V0 belongs to B0, right? So let's just substitute different elements. So what will happen to 0 minus V0? So 0 minus V0 is minus V0. So clearly minus V0 is not 0, hence it does not belong to B0, right? So 0 does not belong to this equivalence class of V0. How about V1? So what about V1 minus V0? Well, V1 minus V0 is just V1 minus V0. Again, this is not 0 and this does not belong to B0. What about V0 plus V1 minus V0, right? This is the other element in Z0. So V0 plus V1 minus V0, well, this is V1 and this is again not equal to 0. Hence, this also does not belong to B0. So you can see that the only element that is equivalent to V0 is V0 itself, and the reason for that is that V0 minus V0 is 0 and this belongs to B0, right? So from this one can conclude that the equivalence class of V0 is the set containing the element V0, the equivalence class of V1 is the set containing element V1, and the equivalence class of V0 plus V1 is the set containing V0 to V1. So one can indeed see that these four equivalence classes are different, and that's why it makes sense to list them separately, right? And now one can ask, what is the dimension of this vector space, right? So for that we have to identify a basis, right? And one can see that the basis for this vector space is the set containing V0 and V1, right? So one can see that every element in this set can be constructed using a linear combination of elements in this set. Hence, this is a basis. From this, one can conclude that beta 0, which is the dimension of H0, turns out to be 2. Is this okay? So this turns out to be 2. All right. So so the first thing we noticed is that in this example, beta p is 0 for all p not equal to 0, whereas beta 0 equals 2. Okay, so this is the answer that we have obtained. So again, I would like to stress on the two parts. One is that you are able to algebraically make sure you will also be able to get this answer. And the second part is, how does this capture the homology or the shape of this simplicial complex that we have over here. Okay, so I'm open to questions on either of them. I'll be, please let me know. If you have any questions, please ask. Yes, Jacob, go ahead.
How does it characterize this shape, like you have said?
How about you tell me, what do you think? Right?
Just 0, 2, there are two matrices, so
Okay, so let's do a quick calculation, right? So let's say there were 3 vertices, right? So your guess is that maybe because there are 2 vertices, beta 0 turns out to be 2, right? So what do you think must be the answer if there were 3 vertices? What do you think your answer must be? So what would beta 0 be for this simplicial complex? What do you think it must be? Yeah, just extrapolate, Jacob, it's fine, right? So here you said there are 2 vertices, hence beta 0 turned out to be 2. Here there are 3 vertices. What do you think your answer must be?
I need to calculate, but I think it should be 3 or.
Okay, so your guess is 3. It's okay. Let's try to do a quick calculation, right? So in order to compute beta 0 is 3, right? So we have to first look at C0, C1 and C minus 1, right? So can you help me? Can you tell me what C minus 1 would be?
0.
0. What would C1 be?
0.
0. And what would C0 be? So let's label this as V0, V1, V2. So what will C0 be?
0, V0, V1, V2.
Okay. V0
V0
plus
plus
V1, blah,
V1.
blah, blah. Okay, let me just write it because it's not that hard. V0 plus V2, V1 plus V2, and V0 plus V1 plus V2, right? These would be the different elements of C0. Do you agree?
Yes.
Okay, so let's quickly compute what Z0 is, right? Or maybe we'll first compute what B0 is because that's easy. So B0 is image of DABA 1. So what would this be? 0, right? So now we only need to compute what Z0 is. What is Z0?
C0.
It's the kernel of DABA 0 and this will be C0, right? Because every element here would get mapped to 0. And I hope you agree that consequently every element in C0 will lie in the kernel of DABA 0, right? And now we can compute what is H0, right? This will be Z0 quotient with B0. And I hope you agree that this you will end up with, something like this, right? Blah, 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 all the way up till V0 plus V1 plus V2. And a similar calculation as we did before will show you that all these equivalence classes will be different. Right? Now I ask you, Jacob, what do you think must be the dimension of this vector space?
The basis is V0, V1, V2.
Very good. So the basis is V0, right? V0, V1, V2, right? This will be the basis for this vector space, and consequently beta 0 in this case will turn out to be 3. Do you agree?
Yes.
All right. Okay, so I hope you are able to see it. Okay, so I mean, I don't want to give you the answer because see, knowing the answer is not knowing or understanding stuff. Okay, but rather I want you to help you come up with a process wherein you synthesize what exactly is happening. Okay, so I have still not told you what this beta 0 is trying to compute, but I have told you how to compute beta 0, and I encourage you to think what is this beta 0 trying to tell us. All right. Okay, so far so good. Okay, so now as an exercise we have finished computing the Betti numbers of this simplicial complex under the usual homology framework, right? So one would like to ask, okay, I understand how to do this in the usual homology framework, but you had also told us something about this reduced homology framework. If we repeat the calculation for this this simplicial complex in the reduced homology, would something else change? Okay, and again instead of telling you why we need this reduced homology, I would again like to do this calculation in front of you and encourage you to think what is this reduced homology helping us achieve. Okay, so that is what will be the discussion for the for the next couple of minutes. But before that, this computing this equivalence classes, okay, will become harder and harder as these the boundary spaces and these kernel the cycle spaces, okay, they become more and more complicated, right? So it makes sense to come up with an efficient way of computing how the equivalence classes in general look like. Okay, so let us sort of digress a bit. So this discussion over the next minute or two doesn't concern necessarily this the homology spaces that we have been studying, but rather it concerns general algebra. Okay, it has nothing to do anything, I mean nothing to do specific to the homology group spaces. All right, so let's say V is a vector space and S is a subspace of V, right? So V is some vector space, V is a vector space and S is a subspace of V, right? So S is a subspace of V, and let's say we define this quotient space in the following way. So this is the quotient of V with respect to S, right? So how do we define this Q then? So if Q is V quotient S, then Q is defined to be the set of all equivalence classes of V where little v is in capital V. And how do we define the equivalence class of V? Well, the equivalence class of V is defined over here. This is the collection of all V prime in V such that V prime is equivalent to V. Equivalently, this is the collection of all little v prime in capital V such that V prime minus V lies in S. Okay, so this is the way we define the equivalence class. And this claim says that the equivalence class can equivalently be represented in the following way, right? So what is the equivalent representation? Well, the equivalence class of V is V plus S, right? So one needs to be careful what is written over here. So this is an element and this is a set, right? So the first question you would like to ask is, oh, this is an element, this is a set. In fact, this is a vector space. So this is a vector space. So how do you add one element which may not even be in S to this entire vector space? Okay, so how do we define this addition operation? Well, the way to define this is in the following way. This V plus S is another set, right? This V plus S is another set and its elements are V plus little s, where little s lies in capital S. So this equivalence class of little v is the collection of all elements of the form V plus S, where V is this same V and S is an element in S. So you take V, add every possible S to this V, obtain the different elements and put them in a set, and that set will correspond to the equivalence class of V. So I hope you are able to appreciate that this gives an explicit way of figuring out what the equivalence class of any element should be. Okay, so let me pause here for a second or two. If you have any questions with regards to the description or the definition or what this claim is trying to tell us, okay, please go ahead and ask. All right, so I don't see any raised hand, so maybe we can advance with the quick proof. So proof is very short, so I thought I'll discuss it in class itself. It's not that hard, right? So our goal is to show that this definition of the equivalence class of V and this definition, which is what we have been studying so far, okay, these two things are one and the same, right? So what is the equivalence class of V that we know so far? Well, it's the collection of all V prime in capital V such that V and V prime are equivalent, and equivalent means that their difference lies in the subspace S, right? So all that we need to show is that this set and this set are one and the same. Okay, that's all we need to show, that this set and this set are one and the same. Okay, so that is what our goal is, right? So so this is what I have written over here. Hence it suffices to show that and two elements V prime and V are equivalent if and only if V prime is of the form V plus S, right? So that is what we need to say, right? So every element in this set, which is V prime, is of the form V plus S. That's all we have to show. But this is trivially true, right? And hence it follows that this representation and this representation are one and the same. Okay, I'll pause here for a second or two. I mean, it may take some time for you all to digest what this means and what this means. If you have understood it, please ask the question now. If not, you may go back home, read a bit about it, and you can ask me later in the class or in some of the forthcoming classes as well. All right. So let me pause for a second or two. If you have any questions on why these two sets are one and the same, please ask. All right. So I don't see any raised hands, so maybe we can advance. Okay, so let's sort of now come back to the discussion on computation of Betti numbers, right? So what we did so far was we looked at this very, very basic example, right? And we computed the Betti numbers associated with this example, but we were, under the usual homology framework. Now we will do the same example, but we will now use the reduced homology framework, right? And we will see how does things change when we work with the reduced homology framework. So what does it mean when we say we are working with the reduced homology framework? It means that C-1 is said to be this Z2 field, right? This is the only change that happens, right? So now recall that C-1 being Z2, okay, this will only affect the computation of HP for P in 0, -1 and -2, right? For every other P, right, CP plus 1, CP and CP -1, okay, these three vector spaces will not change, right? I have only changed one vector space, hence these vector spaces will not change if P does not lie in this set, right? So which automatically implies that even in the reduced homology framework, beta P, okay, will be the same as in the usual beta P in the reduced homology. Beta P in the reduced homology framework will be the same as in the usual homology framework for P which does not belong to 0, -1 and -2. Is this okay? So this must be clear to you. Since these vector spaces do not change, the computations will not change, okay, and hence this statement holds true. So whether you look at the reduced homology or the usual homology, the pth Betti number for P in this set will be the same, right? So we only now have to worry about what happens if P lies in this set, right? So this is what we are going to do now. So now let's look at the boundary case first, which is P equals -2, and let's try to compute does your H -2 and hence beta -2 change in any way, right? So in the usual homology case, the beta -2 turned out to be 0. So let's see if beta -2 turns out to be 0 here as well, right? So let's see what happens. So in order to compute this beta -2 and in particular H -2, we will have to look at so this is C -2, this is C -3, and this is C -1. So here is where the DABA -1 operator will go, and here is where the DABA -2 operator will go, right? And C -1 is Z2, this is 0, this is 0, right? So I hope you can see that kernel, so Z -2, which is the kernel of DABA of -2, this is made up of only 0, whereas B -2, which is the image of DABA -1, this will be 0, right? Now Z2 is made up of two elements, right? And since here you only have 0, so the only way you can map 0 is, you can define this DABA -1 operator is to map both these elements 0 and 1 to 0. Right, so this is how we can define, and consequently it must be the case that B -2 is also 0, From this, based on our previous discussion, it should be easy for you to see that H minus 2 is a trivial vector space, and hence even in this case it turns out that beta minus 2 is 0, right? So hence it turns out that beta minus 2 is also 0. So in the reduced homology or in the usual homology, beta minus 2 turns out to be 0 for us in this special example, right? So in this special example, that's what it turns out. So now it remains to compute beta minus 1 and beta 0. So let's compute this beta minus 1, right? So again, in the previous case, in the usual homology case, this was 0. So let us see if it turns out to be 0, right? So I want you to appreciate two things. One is whether beta minus 1 in the reduced homology framework, does it turn out to be 0 first? And the second is the reason it turns out to be 0, is it the same or not? Okay, so we should not blindly write something is 0 just because we guess it must be 0, right? So we have to make sure the calculations correspond to what we are trying to guess, right? So let's look at this p equals minus 1 case. So p equals minus 1 means we have to look at these three vector spaces, C0, C minus 1 and C minus 2. So this is the DABA 0 operator and this is the DABA minus 1 operator, right? So first let's look at the B minus 1, right? So B minus 1 is the image of DABA 0, right? So maybe I'll write this a bit down. So the elements here are 0, V0, V1, V0 plus V1. C minus 1 is made up of these two elements, and C minus 2 is made up of 0, right? So this is mapped to, so if you recall the DABA 0 operator in the reduced homology framework, right? So this sort of maps summation Ci Vi to summation Ci, right? This is how we had defined the DABA 0 operator in the reduced homology case. So from that you should be able to figure out that 0 gets mapped to 0, V0 gets mapped to 1, V1 gets mapped to 1, but V0 plus V1, this also gets mapped to 0. Okay, so this is how we define it. So from this and one can also see that 0 gets mapped to 0 under this DABA minus 1 operator, right? So from this operation it should be clear that your B minus 1, right? So B minus 1 turns out to be both, I mean it includes both 0 and 1, right? And similarly Z minus 1, okay, so I should mention this. So this is how the map is defined. So Z minus 1, this also is defined, I mean this is the set which also includes the two elements 0, 1. Okay, so let me pause here for a second or two. I'll sort of allow you to look at these different calculations, and if you have any questions please ask. Okay, so what is important is that here B minus 1 turns out to include these elements 0 and 1, and Z minus 1 also turns out to include these elements 0 and 1, right? So if you sort of have any questions on how we arrived at these formulas, please let me know. All right, so I don't see any raised hands, so maybe we can advance. Okay, so what we have observed is that this B minus 1 turns out to be this, and Z minus 1 turns out to be this, right? So so now let's look at what H minus 1 should be. It will be made up of the equivalence classes of these two elements, that is the equivalence class of 0 and the equivalence class of 1, right? So although we write it like this, it's always important to make sure that these two equivalence classes are one and the same, or are they different. So that is something we always have to verify, right? So from the previous claim, we if you saw, we said that this equivalence class of V is V plus S, which is the subspace with which we are taking this quotient operation. So this is little v plus little s such that little s belongs to this subspace, right? So from this one can see that the equivalence class of 0 will be 0. So recall what b minus 1 is. So this is the space with respect to which we are taking the quotient operation, right? So what is the equivalence class of 0? Well, it is 0 plus 0 comma 0 plus 1, right? So I hope you agree that this will be 0 comma 1, and the equivalence class of 1 similarly would be 1 plus 0 comma 1 plus 1, and which will again be 0 comma 1. So you can see that in this case the equivalence classes turn out to be one and the same, right? So that's why although this h minus 1 and h minus 1, to begin with, we may write the equivalence class of 0 and 1 separately, but we notice that these two equivalence classes are one and the same, and hence it doesn't make sense to write them or repeat these elements. Hence it follows that h minus 1, okay, h minus 1 will only include one element, which is either the equivalence class of 0 or the equivalence class of 1. Okay, so it is important to note that I could have as well written it as equivalence class of 1, right? And think of this as the additive identity, right? So think of this as the additive identity. Think of this as the additive identity. And why can I think of this as the additive identity? Well, the reason is that 1 plus 1, this is 1 plus 1, and this is equivalence class of 1 itself, sorry, equivalence class of 0, right? So 1 plus 1 is 0, and hence this is equivalence class of 0. But we saw above that the equivalence class of 0 is the equivalence class of 1, right? And hence one can see that this relationship actually holds true, and consequently one can think of this 1 as the additive identity itself, right? And hence one can again conclude that this h minus 1 over here is actually a trivial vector space. Is this okay? So from this one can conclude that beta minus 1 again turns out to be 0. Right. So my point is that although beta minus 1 turned out to be 0, notice that the calculations were quite involved in the reduced homology case, but nevertheless beta minus 1 turned out to be 0. Is this okay? So that is something that is interesting to note, but at the same time one should also appreciate that the calculation were not the same, right? So the reasons for beta minus 1 being 0 are not the same in the usual homology case and the reduced homology case. Okay, so let me pause here for a second or two. If you have any questions with regards to what I said, please let me know. Please let me know if you have any questions. Please don't hesitate. All right, so I don't see any raised hands, so I'll presume that most of you have understood these things. Okay, so let us advance with the last thing, that is p equals 0. Okay, so what is the story so far? Okay, in the usual homology case, right, in the usual homology, Betti p was 0 for all p not equal to 0, but beta 0 turned out to be 2, right? And in the reduced homology, the story so far is that beta p is 0 for all p not equal to 0. We don't know what beta 0 is, right? So this is what remains to be computed, and let's try to do that computation, right? So now we are in the p equals 0 case, and we are now going to spend some time computing this beta 0 value, right? So again, let's try to summarize that in order to compute beta 0 and in particular h0, we have to look at these three vector spaces, that is c1, c0 and c minus 1, right? So c minus 1 is z2, right? And this will be 0, v0, v1, v0 plus v1, right? This is your set. This is your set. And so maybe I'll write Z2 also as made up of two elements, and then this will be an element 0. So would one of you like to volunteer to help me do this calculation? I'll help you, but please volunteer. So this is where the DABA1 operator is, and this is where the DABA0 operator is. Would one of you like to volunteer? Please let me know. Please volunteer, I'll help you. I don't see anyone who has raised his hand. So shall I pick one of you to help me? So let's see. Maybe someone who I haven't, had a chance to discuss. So Minali, would you like to help me? Minali, are you there? Okay, I don't see Minali. I cannot hear Minali. Pankaj, would you like to help me?
Yeah, sure.
Yeah.
So
So
DP here.
Yeah.
DP here will be 0.
Can you repeat? What will be 0?
DP 0.
So P here is 0. So do you mean Z0? Is that what you mean?
Yeah.
So how about you tell me first? Let's begin by by looking at the maps. Where will the 0 in C1 get mapped to in the elements in C0? Where will this 0 get mapped to?
0.
0. Very good. And what about DABA 0? Where will the different elements get mapped to under DABA 0? How about 0? 0 will get mapped to
0.
0. Very good. What about V0?
V0 will map to 1.
Very good. What about V1?
Again 1.
And what about V0 plus V1?
It will map to 0.
Very good. Okay, so this is the story. Now let's look at Z0. So this is the kernel of DABA 0, right? So this is the kernel of DABA 0. So you have to tell me all those elements which got mapped to 0. So what are those elements?
0 and V0 plus V1.
Very good. So you can see that this was different to what you said. Do you agree?
No, I was about to add the other one actually.
All right. Okay. So then you are right. So you can see that Z0 is 0, V0 plus V1. What about V0? So what is V0? So this is the image of DABA 1. So image of DABA 1 turns out to be just 0, right? Because
0.
That's the only element that gets mapped to. All right. So now you have to tell me what H0 is. What should I write?
H0 should be, let's start with 0 and V0 plus V1.
So these are the two equivalence classes. So let's make sure that they are different. So what is the equivalence class of 0?
0 plus 0.
So it is 0. And what else would it include? Would it include V0 plus V1?
I don't think so. I think V0
so the question
plus
I'm
V1
asking is 0 equivalent to V0 plus V1. That is the question. Okay. So your answer is no.
No.
Can you justify why?
Because if I take the inverse of V0 plus V1.
Yeah, so how about we look at V0 plus V1 and subtract 0 from this? So this will be V0 plus V1, right? And this does not belong to V0. Is this okay?
Yeah.
Right. So that's the reason the equivalence class of 0 will only have 0. And similarly, what will be the equivalence class of V0 plus V1?
It will be V0 plus V1.
Very good. Okay, so now we have verified that these two sets are different, and hence it makes sense to write them in this fashion, right? So now the last thing you have to help me compute, Pankaj, is the dimension of this vector space. What do you think is the dimension of H0?
It should be 1.
1. So you have to justify. Why is it 1?
Because 0 is not linearly independent.
0 is not linearly independent. So is there some other way you know how to compute the dimension of a vector space? Have you studied something related to bases and things like that?
Yeah.
So give me a basis for H0 which has one element, because your answer was that the dimension of this vector space is 1. Do you agree?
Yeah.
So give me a basis.
Basis should be, I think, V0 plus V1.
So the equivalence class of V0 plus V1, right? So the way we have to quickly verify is that using this element, you can construct both these elements using linear combinations, right? And the scalars have to come from your Z2 field, right? So it is easy to see that 0 times V0 plus V1 is 0 times V0 plus V1, and this is the equivalence class of 0. So you can see that in this fashion we can create this element, and similarly one scalar product V0 plus V1, this is one scalar product V0 plus V1, and the equivalence class of this, and this is V0 plus V1. Is this okay? So you can see that by using scalar combinations, you are able to create all these elements, and consequently, the dimension of H0 is 1. Thank you, Pankaj. Okay, so you can see that we managed to finally show that beta 0 is 1. All right. So I hope the purpose of asking one of you to volunteer is that to make sure if I see some of you making some mistakes, okay, I can make sure you understand why those mistakes are made. When I only teach, it's not clear what are the issues that some of you may confront. Okay, so that's the reason, was the only reason to make one of you volunteer. Okay, and next time please volunteer on your own. I don't want to force anyone to volunteer. All right. Okay, so beta 0 is 1. So one part of the story is, you should know how to compute these Betti numbers. The second part of the story is to interpret the result. So let's now focus on the interpretation. So the interpretation is in the usual homology and in the reduced homology, what changed? Okay, so in the usual homology, your beta p was 0 for all p not equal to 0, and it was 2 for p equals 0, right? Or let me write it this way, beta 0 was 2, right? On the other hand, in the reduced homology case, beta p was 0 for all p not equal to 0, whereas beta 0 in this case turned out to be 1, right? So you can see that the only difference actually occurs in beta 0, and in general one can show that if you represent beta p tilde as the Betti numbers in the reduced homology case, then, and beta p to be the usual homology, then beta p tilde will equal beta p for all p not equal to 0, and beta 0 tilde, sorry, beta 0 tilde is beta 0 minus 1, right? So I want to write something like this. That's why I sort of said when we are working in the reduced homology case, okay, once in a while we may represent the Betti numbers derived in the reduced homology case with the tilde notation. This is only when we want to talk about the Betti numbers of the reduced homology and the usual homology side by side. Okay, that's why I'm using some different notation. So one can in general show that beta p tilde is actually what should I say, same as beta p for all p not equal to 0, whereas in the p equals 0 case, beta 0 tilde turns out to be beta 0 minus 1, right, as we saw in the previous example. So one can in general see that this relationship actually holds true, right? So the question then is, why is this reduced homology needed, right? So first of all, the word reduced makes sense because all the Betti numbers except the 0th Betti number, okay, so they are one and the same, but the 0th Betti number reduces by 1. So it is because of this reason that the new Betti numbers are called the reduced Betti numbers. Okay, so that's the first reason. Now you may ask, okay, why do we want this beta 0 to be reduced by 1? Okay, so that I will encourage you to think Okay, maybe over the next class also I will not give you the answer, but I will encourage you to think. But I want you to, pay attention of what is happening. In particular, I will give you some hint. I want you to interpret what happens to the Betti numbers in the higher dimensions and compare it to the behavior of the zeroth Betti number. Okay, so the bottom line now is that in the zeroth Betti number case, that is the only one that changes. Sorry, when we are working with either the usual homology or the reduced homology, only the Betti zero changes. Now, why do we want it to change in a certain sense? For that, I would like you to pay attention to what happens to the behavior of Betti numbers in the higher dimensions. Is this okay? Just a minute. All right. Okay. So now, as you can see, my, my page is blank. So the reason was I wanted to do some example on the fly. Okay, I didn't want to sort of come prepared with an example. So this is example 2, right? So what we saw in the first example was a simplicial complex of the following kind. So now what we will do is we will go a step beyond and, try to do something on the fly. So let's say, but this time, let's see if we can have something in non-trivial in the higher dimensional space. Okay, so let's say our simplicial complex is something like this. Okay, so let's say it has something like this. Okay, so let's say this is V0, V1. So what I'll do is I'll not call this as V0, V1, V2. I'll just call this as 1 or 0, 1, 2, and 3. Okay, and this triangle is present. Okay, so maybe what I'll do is so I will define this abstract simplicial complex. So delta over here. Okay, so this includes these 4 vertices 0, 1, 2, 3, and it includes 1, 2, 3, 4, 5. So 5 edges 0, 1, 0, 2, 1, 2, and 0, 3, and 2, 3. Okay, and it, in addition, it includes this triangle 0, 1, 2. Okay, so this is the simplicial complex that we have, and the question is compute the homology of this simplicial complex. Okay, so now as you can see, there is one hollow hole over here, and then there is one filled hole over here. So if you intuitively looked at this, and if someone asked you to guess how many holes of dimension 2 are here, I hope you agree that, based on this hollow region, your answer would be 1. So there is one 2-dimensional hole. Now, if I ask you how many 1-dimensional holes are here, again, I haven't defined it for you, but as I said before, I encourage you to, constant be on the lookout for what could be an appropriate definition of 1-dimensional holes. Is this okay? But nevertheless, you have a recipe to compute the Betti numbers of different dimensions. Okay, so we will do that as an exercise now. Okay, so what is our goal? Our goal is to compute beta p for all p in Z, right? So let's try to do that. Okay, so the first is for all p bigger than equal to so let's see, bigger than equal to 4, right? So can one of you volunteer and tell me what happens for p bigger than equal to 4? What do you think beta p must be? Please volunteer. It's not that hard. This is the easiest case. If you wish to volunteer, this may be the right time to volunteer. Yes, Durjati, go ahead. What do you think should happen for p bigger than equal to 4?
That is beta p must be 0.
Beta p must be 0. Can you quickly justify why beta p must be 0?
Because maximum dimension is 2, I think. For
Maximum
C,
dimension is 2. Yes. So what?
C3 is 0 and C4, C5 all
Very
are
good.
0.
So in general, Cp plus 1, Cp and Cp minus 1 for p bigger than equal to 0, they will all be trivial. Is this okay? Right. So they will all be trivial. So this is how the story will look like. And since they will all be trivial, I hope you agree that Zp, Bp will also be trivial. And from this one can conclude that Hp must be the trivial vector space, and hence beta p turns out to be 0. right? And in the same way, I will not do it, but you can verify that for all p less than equal to, so let's see, -2, right? Beta p will turn out to be 0, right? So now what remains is to compute beta p for p in, so for p in -1, 0, 1, 2, and 3. Okay, so I will leave a computation of 3 as an exercise, and we will focus on these 4 p cases, right? So first, let's so you don't have to compute it in any order, right? But let's look at the easy case. So the easy case is p equals 2. Okay, so can one of you please volunteer in the p equals 2 case? So maybe I'll draw this simplicial complex here. So this is what it is, and what are the vertices? 0, 1, 2, 3. So this is 0, 1, 2, 3. Okay, can one of you volunteer and tell me what will happen in the p equals 2 case? Please volunteer. So you have to tell me what beta 2 is. Please volunteer quickly. It's not really hard. Please volunteer. Mehul, would you like to volunteer? Mehul, are you there? Looks like half the students. Mehul, are you
So
there?
it should be 1, I think.
Beta. Okay. So beta 2 should be 1. Is that what your answer is?
Yes, sir.
Okay. So how about we try and do this formally? So how do you compute beta 2? So what is the definition of beta 2? It's the dimension of H2, right? So we have to first look at what H2 is. So how do you define H2? Can you tell me the definition of H2? So it is Z2 quotient B2, right? This is how we define H2. Do you agree?
Yes, sir.
Okay, so what is Z2? So in order to understand Z2, we have to first look at, so let's try to understand. So this is C3, this is C2, this is C1, right? And Z2, so what is Z2? So Z2 is the kernel of DABA 2, and B2 is the image of DABA 3, right? Okay, so what is, okay, maybe I'll move this slightly over here. Okay, and let's see. So can you tell me what is C3? Mehul, can you tell me what is C3? Mehul, would you like to like some time to think?
Yes, sir.
Okay, would anyone else like to volunteer? Moksha, would you like to volunteer? Moksha, are you there? Okay, there is no response. Dinesh Rathod, would you like to volunteer?
Hello, sir.
Am I audible, Dinesh?
Yes, sir.
Yeah, would you like to volunteer?
So in C3,
Yeah, C3 should be what?
0, comma,
0, comma.
uh,
It's
C0,
the chain. It's made up of these 3 chains. So how many 3-dimensional faces do you see in this simplicial complex?
1, sir.
One 3-dimensional face. Which is that 3-dimensional face?
V0, I mean 0, 1, 2, 3.
So see, I hope you remember what the simplicial complex was. It only included 4 vertices, 5 edges, and 1 triangle, right? So a 3-dimensional face is this 0, 1, 2, 3. I didn't say that that is a face in the simplicial complex.
Okay, sorry.
So what should your definition of C3 be?
0.
0. Okay. What should be the definition of C2?
0, comma.
0, comma.
0, 1, 2.
That's it, right? So these are the two elements that will be there in C2. Do you agree?
Yes.
Okay, what about C1?
0, 1.
Okay, 0, 1. So let's just draw it properly. So let's draw it slightly big. So this will be, okay, so what all will be the different things? So you said 0. Okay, what else?
Sir, can you show me the simplicial complex?
Yeah, I have showed it. Can you see it now?
Uh,
Are you
0.
able to see it?
Yeah.
Okay. Yeah, go ahead. 0.
2.
How can 2 be an one face? Like, so 2 is a vertex.
Okay,
See,
0.
we are now talking about C1, which is the collection of all one chains.
Yeah, sir.
Okay.
0, 1.
0, 1, very good. Then 1, 2, then
2, 3.
2, 3. And let's me write all the edges. Okay, so 0, 2, and what else is remaining? 0, 3. Okay, so these are some of the one chains. Are there some more?
5 edges, sir. Yeah.
5 edges, that's it. But C1, is it a set which only includes 5 edges, or does it? It's a set. C1 is a set of one chains. Have you
yeah.
accounted for all one chains?
I mean, individual vertices as well.
No, what is a one chain? One chain is all possible linear combinations, right? So it is AI sigma I such that AI belongs to Z2 and sigma I belongs to F1 of delta, right? This is what C1 is. This is how you define C1. Do you agree?
Then 0, 1 plus 1, 2.
Very good. 0, 1 plus 1, 2, 0, 1 plus 2, 3, blah, 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 all the way up till 0, 2 plus 0, 3. Do you agree? All possible two, two edges you have to take and, form a sum. What else would we have?
Taking 3 edges.
Very good. So 0, 1, 1, 2, 0, 3, and so on. And what would be the final one? I'm not going to list everything, but what would be the final one?
Of all the edges.
Very good. 0, 1 plus 1, 2 plus 2, 3 plus 0, 2 plus 0, 3. Is this okay? So this is how your C1 looks now, right?
Yes, sir.
All right. So now maybe I'll, change this slightly so that it helps me in the next discussion. So 0, 1 plus 1, 2 plus 0, 2. All right. Thank you, Dinesh. Maybe I'll ask someone else to volunteer. Lakhan, would you like to volunteer? Lakhan, are you there? Please unmute yourself if you are there. Okay, I cannot hear Lakhan. Ganesh, are you there?
Yes, sir.
Okay, can you please volunteer, Ganesh? So can you tell me how do we define these maps? Like this is Daba 3 over here, right?
Yeah.
This is Daba 3 and this is Daba 2. Can you tell me how Daba 3 will map this 0?
Yeah. So Daba 3 will map 0 from C3 to 0 from C2.
Very good. Okay, what about Daba 2? Where will
Daba
0
2
get mapped to?
Yeah, 0 will get mapped to 0.
Very good. And what about 0, 1, 2? So recall that this is a face, right? 0, 1, 2 means a face, right? Actually, this means the set 0, 1, 2, but I'm being a bit sloppy here and writing it as 0, 1, 2, right? And I want you to tell me where would 0, 1, 2 get mapped to in C1?
So it will be the sum of the coefficients. So 1 plus
Sum
1.
of the edges or the boundary faces of this triangle, right? So what is it?
So it would be 1 plus. So I'm a bit confused here. So it should be the sum of the coefficient, right?
No, drop one index only.
So see, Daba 2 of 0, 1, 2, right?
So
This
it will
is
map to 0, 1.
Yeah, so you have to drop one vertex at a time. See, this is not the Daba 0 operator where you sum the coefficients, right?
Right.
So,
right. Yeah, got it.
okay, so this is the Daba 2 operator. So I hope you agree this is where it will get mapped to, right? And I am written this sloppily over here. Do you see this?
Yeah.
So this is where it will get mapped to. Does that sound good?
Yes, sir.
Okay, so now you have to tell me. So this is the mapping. Now you have to tell me what Z2 is. What is Z2?
It will be the kernel of Daba 2.
And what is it from this figure? Can you tell me what it is?
Yeah, it's 0.
0. Very good. What is B2?
It will be the image of Daba 3 and it would be 0.
Okay, so from this, can you tell me what H2 is?
It is Z2 quotient B2, which will again 0.
0, right? So but it's the equivalence class of
Equivalence
0.
class of 0, yeah.
Right? And so one can again see. So from this, what should be beta 2?
It's 0.
Very good. Okay, so this is how you have to calculate. While I haven't managed to calculate everything, but I encourage you to tell me, I mean, go ahead and do this exercise on your own and see what do the Betti numbers of this abstract simplicial complex turn out to be. Is this okay? So, I did the very basic exercise. Okay, so a teacher always has this luxury of taking the most basic exercise and do it in front of the class, right? However, if I have done a job well, you should be able to build upon the discussion in the class and be able to compute the homology of this simplicial complex that is given over here. Is this okay? So that you should be able to do, and from this point on, if anyone gives you a simplicial complex, you should indeed be able to compute its Betti numbers. Okay, so this may be a good point to stop. All right, so I have stopped the recording.